Hey everyone, so welcome to this talk. So I'm Jonas, I am part of the Postman Open Technologies team where I work exclusively on AsyncAPI. And this talk I'm going to give is about schema complexity in schema formats. So within AsyncAPI we have something called schema formats where you can explicitly say which type of schema format you use to specify your message payloads. By default, this value is the AsyncAPI schema object. It's something you might be used to in OpenAPI, where in 3.0 it was the 3.0 OpenAPI schema object. But this value is something that you can change, and it's something that we have support for multiple other values. So I'm going to introduce two of those. I'm going to introduce JSON schema, and I'm going to introduce something called JSON type definition, which is two extreme differences between them as well. And then I'm going to talk a little bit about how that complexity plays out in tooling and how we kind of try to mitigate those complexities. So JSON schema. By default, if you haven't heard about this keyword before, you would use this AsyncAPI schema object. It's just a simple superset of the JSON schema draft 7 specification. It's the same with the OpenAPI 3.0. JSON type definition, however, is a structural way of defining the structure of your message payload, where in JSON schema and the subsequent other schemas, it's constraint language, where you constrain your data. And I'm going to show exactly what I mean later. So yeah, JSON schema. If you wanted to just use pure JSON schema instead of the AsyncAPI schema object, you could choose to define it with this value. That means that instead of having this superset, you just use the simple JSON schema core specification for defining your message payloads. And what JSON schema is, and it's a bit complex subject, which I'm hoping I can clarify a bit. So in JSON schema, it's about constraining data, or JSON data. So that means that when you say something like type Boolean, it means that you accurately validate Boolean values in JSON and invalidates other values that doesn't comprise of this. We, of course, have multiple different ways or different types. We have both for arrays, we have numbers, integers, we have arrays, I said that. And we have null, and then we of course also have object. Now, by default, if you just say, well, it's a type object, it can be an arbitrary object that it accurately validates. So that means that you can have any properties in there, you can have, and those properties can have any values. But you can of course further constrain that as well. So you can say, well, what if I have this specific property, then I want it to validate against the following schema. So for example, in this case, if there is a property called display name, then I want it to validate against a string. And that means that if the display name is a different value, for example, a number, it would be an invalid data. So I want to deep dive into this validation thing and where you constrain data, because this is where a lot of the complexity comes in when it comes to tooling. So what I mean by validation is that you kind of iterate, and this is what the specification tells us, that you iterate over all of these properties or all of these keywords one by one. And then you say, okay, I expect there to be a type object on my input data. Well, in this case, it is an object, so it's valid. And you still iterate over, and then you go into all of the properties. Is there a display name property? There is. Okay, so I validate it against my schema. It is a string, and as we can see on the right side, well, it's a string value, so it's valid. And we kind of iterate down, and then we get to email. And when it comes to email, well, we are using a format here, or we expect a specific format for the string. In this case, we expect an email, and in this case, our value is test, which is, well, not an email. So it invalidates that result. That means that now we mark the entire enclosing schema as being invalid. And it goes up until you get to the root object. And now the validators can say, well, this is an invalid data against this schema. Don't do this in production or in any teams. I'm just using it to emphasize what a constraint language means. So in JSON schema, you have multiple other keywords. In this case, we can use not to negate the validation result. So in this case, if we start off where we left off in the last example, we have this invalid validation result. Now what the not keyword does is, well, it negates that invalid result and makes it valid. And then it goes to the next one, and it negates it again. So it's basically the same as having none of these not keywords, but it's possible to do. And that's the kind of problem with JSON schema, that it is a constraint language. And if there's one thing I want you to get out of this talk and remember, is that JSON schema is a constraint language and not a way to define the structure of your data payload. So then there's JSON type definition. So this is where you actually define structure, but it's impossible to do complex validation, such as conditional validation rules and other kinds of keywords. So in AsyncAPI, we actually don't have a specific format for JSON type definition, but it can be an arbitrary value. So in this case, I'm just using JDT to explicit. Now, all of the tooling must be able to be extendable to understand these things. So this means that we try at least as much as possible to have our tools be able to understand whatever format you want to use. So in this case, JSON type definition also has a lot of regular type variants for your data. So in this case, we also have the string variants, but we also have more precise definitions of numbers and floating points and booleans and even some timestamp stuff. And we also have some more complex forms of structures. So this means that we can have empty forms which are in the standard also mapped to a programming language, which in JSON schema don't have anything of that kind. So that means that we also have something where we can specify for properties within a JSON object, for example, what is the structure of a specific property. So if we compare the two things, the JSON schema is on the left side and JSON type definition on the right side. We can see that they're very, very similar in syntax. But the JSON schema is kind of misleading in many ways because it's both validation rules, but it's also a kind of one-to-one to structure. And I'm going to get a little bit into that as well. But yeah, also schema formats. I wanted to mention that we also support Avro, RAML, and we are looking to in the future to support protobuf, for example, or even XSD schemas. It is a little bit tricky with XSD and protobuf for that matter, because it's not JSON compliant. So, and the entire AsyncAPI specification isn't JSON. So having that mapping to a JSON format is tricky. But we are looking into it at least. So I want to talk a little bit about tooling. And I want to talk about code generation, and I want to talk a little bit about documentation. So in JSON schema, when you use JSON schema and you wanted to use it in code generation, you are kind of trying to map it to, you want a structure that represents any of the valid data that the JSON schema validates. That is what you're trying to get at. And this is the tricky part, especially if you don't ignore keywords. Because if you use any arbitrary JSON schema as an input, you will have these problems because you must support not, you must support if and else and then, and you must support all of, one of, any of, etc. And this is what creates the complexity. But if you ignored all of those keywords and only focused on the structural keywords, it's rather easy to map it to a structural language. But even mapping it to a language, if you try to map JSON schema to a language, it's the same reason why we have so many programming languages. It's not as easy as saying, well, I want interfaces, that's the standard. No, because some people want a class. And in some languages, it's different from what it can achieve. Of course, you don't really have that in Java, for example. It's most likely a class that you want out of it. But it just shows that there are so many options that you have to take into account. It's the same with enums. In TypeScript, it's possible to use a string union. But you can also have it as an enum type. So you have to create the tooling that allows this to be customizable by the users. So we're kind of splitting up code generation into two sections. We split it up into a library type code generation, and we split it up into a model generation. And what I mean by this is that in library generation, it's often about creating this scaffolding library project where you kind of just want to have the message payload somewhere in there where you want to access a resource. So that means that you must be able to, based off of your message payload, get a type out of it, as well as the further model generation that are created. So in AsyncAPI, we created this Modelina tool that is within the AsyncAPI organization. So it's entirely open sourced. And I want to talk a little bit about how we do things there. So within Modelina, we don't only support AsyncAPI, we also support for a number of other formats, even OpenAPI, or just raw JSON schema documents as inputs. And we can use this to then generate models. And not only just models, but we want to both make it customizable, also as extendable as possible. So that means that you can, for example, if you want an extra function within your models, within a specific model, for example, in this case, in a class, you can add that specific function to the model generation phase without actually caring about all of the complexities behind it. You just add your own additional custom function. And that's the extensibility part. We also have a lot of customization through this in order to support these use cases where either you want to generate interfaces or you want to generate classes, and the same with enums, etc. So we have a lot of those customizations as easy as flitching or switching a Boolean as an option. Sorry, I needed to show that as well. Yeah. But yeah, that's the code generation part. So in documentation, all of our documentation tools rely on our parser. Our parser, the way that it handles these complexities with schema formats is that you can extend the parser with custom parsing logic for a schema format. That means that if you want to add some, let's say that you have your own internal schema format that you want to use, you can still add it to the parser and it would be able to understand it. The way that the parser currently works is that we transform all of the different schema formats, RAML, Avro, OpenAPI object, we transform those into the AsyncAPI schema object. And this creates a little bit of a tricky situation down the line. Because when it comes to documentation, when you look at documentation, do we really want to see this when you're trying to figure out which data you want to send or which data you're consuming? Because this is not structure. It's rather hard to see as well. So we're trying to look at how can we solve this dilemma? And we don't have an answer for it yet. But I want to at least make you think about it, and maybe you can even come up with a solution for it. Can't remember what else. Oh yeah. So as anything else in software, there is no single silver bullet. I just want you to think about, and this is something new that is kind of, that you are not able to do in OpenAPI, right? Because that in the new 3.1, it's the JSON schema draft 12, I think, yeah. And in AsyncAPI, you now have this opportunity to use other schema formats. So we're kind of excited to see where that takes us, but also whether that complexity is paid off in the end. I actually don't have much else. Feel free to join us. We are, of course, open sourced, and everything is in a neutral ground with Linux Foundation. So everything that we work on is completely open source, licensed as Apache 2. And other than that, I'll take any question you have regarding AsyncAPI. Thank you.
Yeah, we still have plenty of time for questions. So feel free to ask about AsyncAPI. Great new concept.
Otherwise, you can find me in the booth with Postman. I'll be there at least in a couple of hours, or in a, yeah.
So I have one question. You mentioned about code generation. So you were talking about server side, the server stubs. What about client code generation?
Yeah, client code generation is actually the easy part, at least when it comes to, so the client part is a bit tricky within AsyncAPI because, well, if it's event-driven and you say client, well, it's get a little bit funky. Of course, if you have WebSockets, for example, then it's easier to have that server-client perspective. But a lot of the code generation that we see within servers or server stubs, for example, is that you mix code generation with custom implementations, which is a dangerous treading path to take. But yeah, it's the same. It's the same dilemma with, for example, payloads or message payloads. It doesn't matter whether it's in server stubs or if it's in client generation. It's actually the very same dilemma. Something that I missed and forgot about was that everything with Madalena is in memory as well. That means that you can chain this into other systems and other integrations, even in websites, where you have access to even the properties of the specific object or class that you generate. That means that you can access the very type that it generated and use that in your library generation. So even in your client stubs, etc., to just say, well, I just want message.type, and that's it. Madalena takes care of everything else. So that kind of leaves it as easier to create other code generators down the line, or at least to support all of these protocols that we are looking at supporting, right? So yeah.